A very good morning, ladies and gentlemen. We are almost in the last day of the GAN course, Concrete Microstructure Characterization, and also the International Conference ICICBM 2018. Today we have with us one more special person, that is Dr. Sayed Kumar Das, Professor, Civil Engineering Department, Indian Institute of Technology, ISM Dhanbad, Jharkhand. I request Dr. Bibidas Sir, the organizing chair, to give him a bouquet and welcome him to NITK Surathkal. Welcome you, sir. I now request Professor Narayanan sir to continue his lecture.
Good morning. All of you can hear me? Okay. Last day. Happy, right? Somehow this has to be done, right? Got into the water, now you have to get out of it somehow. Okay, we won't keep you for too long. Okay. That's it. I think the crowd has thinned out. Or it's too early in the morning? Not really. 9 o'clock typically is midday for us in the US. Life starts at 8 o'clock there. Everything starts at 8 o'clock. It goes from 8 to, so everybody works from 8 to 5. All the secretaries and stuff works from 8 to 5. And here when I go to government office in Kerala, if I have to get something, 10 o'clock you go, nobody will be there. 10:30, nobody will be there. 11 o'clock they say, oh, just came, we went for tea. Right? And then on the other side, people complain, oh, why are we not productive? Productivity and time are directly related. It doesn't take a Nobel laureate to tell you that, right? You're more productive when you do stuff over a longer period of time. Okay, so things that you have been eagerly waiting for, compressive strength. So over the last 4 days, we did a journey right from the single particle of cement, from what it contains, how it is made, to how it reacts with water and hydrates, what forms when things hydrate, at what rate does things form, when those form, how does the microstructure form, how do things get organized, and if things get organized in a certain fashion, how do you measure how have they gotten organized, what is the impact of the organization of the material on the properties, how do you measure those properties, what are the right properties to measure and what are the properties that will not give you right quantities, what happens when you put in different materials of different physical and chemical characteristics, how does this structure form, how does that influence the properties. And yesterday we ended with some early age properties, creep and shrinkage and stuff like that, right? So quite a bit of stuff that we've covered, and so finally, so I have only an hour and 30 minutes today. You will be thanking it, right? So at 10:45 we are stopping. I will do only the most relevant stuff now, so most of the things that you know I'm not going to cover. We'll do some relevant stuff on strength and durability, but ask me questions when you have to and we'll take it from there. Okay, so strength is the most valued quantity, not because strength is a great quantity, but because it is very easy to measure, right? Not just very easy to measure, you can impress somebody by measuring something and really breaking things, right? When somebody sees, oh, a cylinder of concrete being pushed, it's exploding, excitement. Okay, so breaking a cylinder, dividing it by area of cross section gives a compressive strength. If you want to do a little bit more, you can do with elasticity, strains in X, Y, and Z direction. Remember I told you about Poisson's ratio, Poisson's effect? So you have strains in all three directions. Even when I push a cube or a cylinder in one direction, I have strains in the other direction also, right? So you can do elasticity theory. Again, if you're interested in structural mechanics, you can do some of these. I don't do this. Okay. Bulk modulus, elastic modulus, all of you know that. I'll skip all of these things. We'll go to the how do different materials behave. So if you do a simple stress strain curve, or maybe I have not switched this on. So it's my problem now. Okay. So if you have different materials, if you have a metal, you know that you have a very high area of linear elastic nature, then you have yielding, and then you see stress strain curve of steel, right? They do that. Glass, very brittle. Concrete, kind of quasi brittle. plastic, viscoelastic, and then you have some elastic modulus and maximum compressive and tensile strength values, Poisson's ratio for all of that. You can have different types of concrete. Your normal concrete generally fails like that. So if you do a compressive stress strain curve of concrete, it goes up, just comes down, right? So normal concrete is fairly brittle. You can have strain softening materials. So if you put in a lot of rubber or a lot of soft particles in concrete, you will get a behavior like the strain softening. You will have, with increase in stress, the strain will start to come down, strain softening. You dump it with a lot of fibers, steel fibers especially. You dump it with 3-4% by volume of steel fibers, you will get strain hardening. So if you get ultra high performance concretes that are supposed to take very high energy, very high impact loads, they're generally going to be strain hardening. So I go back to the materials by design approach. We talked about that, right? Designing the material for a specific function that you want it to do is exactly how this works. Strain hardening. Okay, it's not strain softening, it's strain hardening. You want it to strain harden, or you want it to absorb a lot of energy on impact. Barriers for roads, barriers for planes not to fall over. You want a very strain softening material so that a lot of energy is absorbed on impact. Right. So ductile and brittle, all of you know what the differences between ductile and brittle materials are. A brittle material will go up to failure and you will have no more strain capacity after that. A ductile material can take a lot of strain after failure. So when you design, this happens. Now you do a lot of cylinder testing, right? Cube testing. In the US, we do a lot of cylinder testing, and I gave you some practical reasons as to why cylinders are better. Better in the sense that it's easier to make. And I always, so in the labs typically here, in a concrete lab, you have 2 or 3 technicians and stuff to do things, right? So when I was doing PhD, I make all the concrete. So I'm the cement carrier. When the truck delivers the cement, I carry it on my head or body or back or wherever I can. Sometimes if my professor is free, he also will come and help me. When the aggregate truck dumps in, we shovel all the aggregate and we ourselves sieve. If you have to get fly ash, we'll transport fly ash. In the lab, we weigh things, we mix things. So we are concrete mixers, we mix it. When the whole thing is done, we take the whole thing, we clean it ourselves. Grad students, all of us do it. So we have no help. The technicians are there actually as technicians. They are working on the machines. They are not helping you make or mix concrete, and we don't have, manpower is very expensive, right? Extremely expensive. So out of practicality, it's impossible for me to carry around 150 mm cubes, very heavy cubes. So 4x8 cylinders, 4 inch by 8 inch, 100 mm by 200 mm cylinders, or 75 mm by 150 mm cylinders, much more easier to do. But in terms of mechanical properties, okay, I have to take a step back. Is strength a fundamental property of a material? When I say I have a 40 megapascal strength, do I mean that strength is a fundamental material property? What do you mean by a material fundamental property? A fundamental material property is a property that does not change when I test for something in Mangalore or something in Delhi, does not change when I change the shape of what I test, does not change based on the environment and the humidity and the temperature within limits when I test. So, does strength adhere to any of these conditions? No. Strength is not a fundamental property of any material. Strength is the resistance to stress. The material does not have its own characteristic behavior, it will just resist the stress. So for example, if you change the loading rate, your strength changes. You test faster, you get a higher strength. So basically if you make M40 concretes and you are not really sure it's an M40 concrete, you just tell the guy in the testing lab, just do it very quickly. Do it like an impact load, just crush it, and you will see 45 megapascal strength and you can make everybody happy. Right? So strength is not an inherent material quantity. What is an inherent material property? If you take a material and say, whatever it is, whatever be the shape, whatever be the size, whatever be it, I can know this material will have the same property whether it's in Delhi or Bombay or Madras or wherever, same. What is that material property? No, that's not a mechanical property, right? Specific gravity is a physical property. So that's what's a mechanical property? if you do, how many structural engineers? If you do any analysis in a finite element program of a concrete structure, what are the only two things that the analysis program will ask you? Young's modulus and Poisson's ratio, that's it. Young's modulus and Poisson's ratio are the only elastic parameters that you have which are material properties. When it comes to thermal properties, then you have thermal conductivity. With electrical properties, you have electrical conductivity. Those are all material properties. Strength is never a material property. Therefore, because strength is not a material property, you will get different strengths when you test a cylinder or a cube. So I'll just tell you what happens. So see here, diameter, length is 2 times diameter. Here is the same dimension all through. Okay, now when you test a concrete specimen, and this is something that anybody who does experiments will have to know before you report your strength. If it's a pure axial compression, okay, if an extremely pure axial compression, what do I mean by an axial load? A load that acts through the centroid of the specimen that I have, right? That is pure axial. Now, how many of you can absolutely guarantee that if I take a cube and place it under a compressive testing machine, your cube is a square, typically the platens of the machine are circular, so you look at it and you kind of straighten it out and you do it, right? How many of you can say that it's going to be axial and there's absolutely no eccentricity? You cannot, right? So, you will never have the pure axial case, and if it's pure axial, the stress paths are going to be like this. But what we have, and also one more thing, you are compressing concrete not with concrete. You're compressing concrete with typically steel. Steel has 5 times more elastic modulus than concrete. For the same load, therefore your concrete will deform more and your steel will deform less. Which means at the steel concrete interface there is relative movement, right? Very small relative movement at the steel concrete interface, which means whenever you have a relative movement at the interface, what kind of stresses come in? Shear comes in. So now you are talking about a pure uniaxial compression. You have introduced shear at the ends of your testing, how much ever you avoid. You introduce shear. How does a shear failure happen? That's how shear failure happens. But then, because you are applying a pure axial load, you have some axial force also, because the effect of the platens go away after some time, right? So if you do that, typically you can do a mathematical proof by using a 45-degree angle. You can say that if my diameter is d, root 3 over 2d here and root 3 over 2d here are my shear zones in whether it's a cylinder or a cube. If root 3 over 2 and root 3 over 2, 2 root 3 over 2, which is root 3 times d of 2d is taken away. What is root 3? 1.73. 1.73 d out of 2d is what? Shear, right? You are testing something in compression and 1.73 out of 2 is 7 out of 8, right? 7 out of 8 is roughly 13%. No, sorry, 7 out of 8 is 83%. 83% of your structure of your sample is subjected to shear. What did you tell you were testing? Compressive strength, right? What are you getting? Shear. And you have a little bit of portion that's pure compression. If you have a cylinder, let's talk about a cube. Oops, I don't have a picture. Okay, let's talk about a cube. I don't need a picture. L and L. So what will this shear zone be? Root 3 over 2L and root 3 over 2L. Root 3L shear. How much length do you have total? How much L? You have only a length of L, which means you have an overlapping shear zone. Which means even in the extreme middle of your specimen, while it wants to go away in compression, in tension, your shear is holding up. You see that? Because of Poisson's effect, at least in the cylinder you can see that, and these are all nice ways of explaining what happens. Here, at least in this zone, it's expanding, right? It's expanding, the Poisson's effect takes place and you can use that and you know that's what is happening and that's how failure happens. But if you look at a cube, even in that zone, even while Poisson's effect wants to expand it, your shear is confining it, which means the cube will show you a higher strength than a cylinder. So basically, when you say that I have an M40 concrete and I barely hit 40, you take a cylinder and test, you will have only 35. Okay? So this is again back to the point of why I have been telling over and over that M40, M35, M50 doesn't make any sense, because I can manipulate the way I test and show you what strength it is. Now, standards have come and said, okay, this has to be the type of specimen, this has to be the rate of loading. This is basically like you drive so fast on the road, you have a few cameras, not everybody gets caught. You say you have speed limit and say you can drive only at 80, everybody drives at 120. Do they catch everybody driving at 120? A few people get caught. Standards are deterrents for bad practices. Standards are not guidances for good practices all over the world. And the more we trust standards and the more we rely, and I am in several standards committees and I will tell you how exactly standard committees work. So standards are deterrents for bad practices. Standards are never recommenders of good practice. Good practice comes from knowing what you are testing and why you are testing it. Make sense? So basically the way standards happen is, for example, if I have to do a standard for cement, ASTM 150, there will be a bunch of cement manufacturers sitting there who have vested interest in making sure that the standard favors them, right? You have a bunch of ready-mix suppliers and contractors who have another set of vested interest in how this material should work with them. And in between, there are a few of us like us, doesn't matter who it applies to, we don't care. We want to make sure that things work well. But typically we never get what we want, because the lobby is always much stronger. So everybody, alkali content of cement. We'll say that you have to reduce the alkali content, especially with a lot of alkali reactivity. We have been pushing for a 0.5% alkali content. Cement companies will never allow, they want to make it 0.85. So you come to a compromise of 0.6. Neither here nor there. All standards are neither here nor there standards. You test it like this, somebody doesn't like it, okay, since you don't like it, what do you like? Oh, we can't give you everything that you like, but is it okay if we give you something in between? Okay, move on, we'll work after 3 more years. When the next revision comes in, we'll see what happens. Let a round robin test of several universities, several laboratories happen. And several universities, several laboratories will do the test. But again, round robin tests are a random number of tests, anybody can interpret the results they want, right? So we really don't make a lot of progress from a standardization point of view. So when you cry for a standard, and you always hear, right, IS 456 as, so when I was doing my undergraduate here in when I graduated in 96, 97, IS 456 was 78. IS 456, 1978, 18-year-old standard was what the students were being taught in 1996. Can you imagine that in 18 years nothing has changed in the world? But we are completely okay with it. In the US at least, ACI 318, which is the equivalent for IS 456, changes every 3 years. Religiously changes every 3 years. They keep changing the design specifications, they keep changing different things. And the most changes happen with respect to shear design of concrete structures. Especially when you start reclassifying different zones as earthquake prone zones. So a zone in 2000 might not have been earthquake prone zone, might be zone 3, now it might go into zone 4, so you have to redesign it. So shear design changes a lot. Flexural design has not changed, doesn't have to change. Your maximum usable compressive strain in concrete is 0.003, that doesn't change. You come up with whatever kind of concrete for regular construction, that doesn't change. Ultra high performance concrete, of course, you have to come up with your own standards. It changes for shear, it changes for development length and anchorage, because reinforcement guys are coming up with better and newer rebars and more effective reinforcement. So the anchorage and development length changes quite a bit, and then specifications for columns under biaxial loading. That changes quite a bit because there's a lot of work that's happening on confinement effects in columns under biaxial bending. So you can get more optimized design. Things keep changing every 3 years. But again, the idea is standards are not recommenders of good practice. Why did you use this loading rate? Because the standard said might get you out of jail immediately if you are in a PhD qualifying exam, but will not tell you what the answer for the problem is, right? Why did you kill somebody? Because somebody told me to kill him. That doesn't get you out of jail, right? So you might be okay, face saving, but can't do much. Get the idea of what happens when you do strength testing? So when you do strength testing of cubes, always know that your M40 concrete in another part of the world will only be an M35 concrete or M30 concrete, depending on how you test it. Okay. Mohs circle, all of you have seen this, Mohs failure criteria, tension, tension, compression, 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 tension, compression, tension, compression. So you have all these 4 quadrants. Inside this Mohs failure criteria you are safe, outside this you are unsafe based on compressive and tensile stresses. You look at your compressive strength to be about 10 times the tensile strength typically. Okay, skip that. What happens under compression? So just again a little more emphasis on the point. So if everything is at an atomic level, when you compress things, there should not be any failure, right? Things should come close like this. But like I said, when you compress a cylinder or a cube, what is failing is under tension because of the Poisson's effect. Okay. Secondary tensile stress at right angles, limiting strains of 0.0001 to 0.0002 for concrete to crack and fail in tension. 0.01% to 0.02% to crack and fail in tension. Strains. In theory, when you design, what do you take limiting strain in tension of concrete as? 0, right? So this value is so close to 0, so you do this as 0. These strains will occur at relatively low compressive stresses. That's the very important point. Think about it. To get a strain of 0.01% locally in a concrete specimen doesn't require a lot of stress, right? Because strain is stress over elastic modulus, right? If you have a lower elastic modulus at a localized portion in a cement paste, how do you get a lower elastic modulus at a localized portion? You think of a concrete cylinder or a cube with aggregates and cement paste, and at some little spot you have, remember, strain is a point property, right? Stress is a point property. These are not bulk properties. Like I told you in one of those classes, we average for convenience. We average for our own ease in representing a single number. You will, if I am sitting on this table, if I sit right in the middle of this table, and then you can use my load and whatever be the support conditions to calculate a flexural strength, right? Does it mean that flexural stress is the same all through the table? No, right? You know where the location is. Similarly, if I have a cube that's under compression, you do load divide by cross-sectional area. What is the cross-sectional area that you're considering? The area of the concrete. Now, if you take that area, that concrete specimen, put it under a microscope, does that all the area is solid? I showed you yesterday. So, are you accounting for that change in cross-sectional area when you calculate this stress? No, right? So, basically you can have very high localized strains if the elastic modulus of a particular region is low. See that? Stress, for the same stress, a low elastic modulus will give you a high stress. How can you get a low elastic modulus in a particular zone? Very near a void, what will happen? What is the elastic modulus of a void? 0. Which means very near a void, your elastic modulus is going to be very low. Which means the stresses in that point is going to be very high. We call it stress concentrations, right? You can have stress concentrations in the material. Because of that stress concentration, a 30 megapascal stress that you applied, that little area is seeing about 100 megapascal stress. Have you studied the idea of fracture of notches, right? If you have a notch and you apply a certain stress far away from the notch sees a much higher stress. If it's a pure circle, if the notch is a pure sphere, it will see how many times more the stress? 3 times, right? So if you apply a 30 megapascal, the notch will see a 90 megapascal stress. Now, if your concrete in that local area is seeing a 90 megapascal stress, for a concrete that you designed for 50 megapascal, what is it going to do? Locally, crack, right? You get the idea. All of you get the idea. It's going to crack locally. So, to get cracking in concrete, you don't need to apply a lot of stress, you get cracks. Now what happens when some cracks form, when some initial cracks form? You have a localized stress. What is a crack? I told you yesterday, a crack is a mechanism by which concrete relieves its local stresses. Now think of a chain with several links in 2 dimensions. When one link in one area breaks, the chain is not breaking completely, right? And if you're still pulling it, what happens to the bond around it? They carry those appropriate loads, right? Load starts to share. See that? So when you have a localized crack, that area is not taking a load. What is happening is, the point next to it is taking a higher load, higher stress, which means that part is now stressed more. The chances of that part failing now becomes higher. That keeps propagating, and therefore micro cracks propagate to form a macro crack, and therefore it fails. So you need only a statistically probable crack that can localize and grow under a certain stress to fail your specimen. And if you have a bigger micro crack to start with, no matter what the strength in the remaining parts of the concrete are, no matter what the average strength of the concrete is, you will get failure. Therefore, failure is also a local property, which is very important. One more reason why compressive strength is a bogus quantity. Because in real life, when failure in a column happens, you can go and core another sound portion of the column and you can still prove that that part is very strong. Whereas locally it would have failed. A bridge deck would have failed locally. You can go core at the extreme ends where it did not fail, it will still meet the compressive strength. Is it good enough? Failure is a local phenomenon, and